Episode 17. Title of the Radio Enabled Learning course is Energy Physics. Unit 5. Solar Energy. In this episode and in this Unit 5, we will discuss about solar radiation and its measurements, solar cells for direct conversion of solar energy to electric powers, solar cell parameters, solar cell electrical characteristics, efficiency, solar water heater, solar distillation unit, solar cooking, and finally solar greenhouse concepts. First, we will discuss about solar radiation and its measurement. In general, the energy produced and radiated by the sun, more specifically, the term refers to the sun's energy that reaches the earth. Solar energy received in the form of radiation can be converted directly or indirectly to other form of energy such as heat and electricity, which can be utilized by man. Since the sun is expected to radiate at an essentially constant rate of a few billion years, it may be regarded by an inexhaustible source of useful energy. The major drawbacks to the extensive application of the solar energy are the intermittent and variable manner in which it arrives at the Earth's surface, and second one is the large area required to collect the energy at a useful rate. Experiments are underway to use this energy for power production, house heating, air conditioning, cooking, and high temperature melting and metals. Energy is radiated by the sun as electromagnetic wave, of which 99% have wavelength in the range of 0.2 to 4.0 micrometer. Here 1 micrometer is 10 to the power minus 6 meter. Solar energy reaching the top of the Earth's atmosphere consists of about 8% ultraviolet radiation, that means short wavelength less than 0.39 micrometer, 46% visible light, that means 0.39 to 0.78 micrometer, and 46% infrared radiation, that means long wavelength more than 0.78 micrometer. Next, we move on to solar constant. The sun is the large sphere of very hot gases, the heat being generated by various kinds of fusion reaction. Its diameter is 1.39 into 10 to the power 6 kilometer, while that of the Earth is 1.27 into 10 to the power 4 kilometer. The mean distance between the two is 1.50 into 10 to the power 8 kilometer. Although the sun is large, its substance an angle of only 32 minutes of the Earth's surface. This is because it is also a very large distance. Thus, the beam radiation received from the sun on the Earth is almost parallel. The brightness of the sun varies from its center to its edges. However, for engineering calculation, it is customary to assume the brightness all over the solar disk is uniform. As viewed from the Earth's surface, the radiation coming from the Sun appears to be essentially equivalent to the coming from a black surface at 5762 degree Kelvin. The rate at which solar energy arrives at the top of the atmosphere is called solar constant, capital I suffix SC. This is the amount of energy received in the unit time on a unit area perpendicular to the Sun's direction at the mean distance of the Earth from the Sun. Because of the Sun's distance and activity vary throughout the year, the rate of arrival of solar radiation varies accordingly. The so-called solar constant is thus an average from which the actual values vary up to about 3% in either direction. This variation is not important, however. For most practical purpose, the National Aeronautics and Space Administrations, that means we popularly known as NASA, standard value for the solar constant expressed in three common units is as follows: 1.353 kilowatt per square meter or 1353 watt per square meter, 116.5 Langley, that means calorie per square centimeter per hour, or 1165 kilocalories per square meter per hour. 1 Langley being equal to 1 calorie by centimeter square of a solar radiation received in one day. 429.2 BTU per square feet per hour. The distance between the Earth and the Sun varies a little through the year. Because of this variation, outside of the Earth atmosphere, flux also varies. The Earth is closest to the Sun in the summer and farthest away in the winter. This variation in distance produces a nearly sinusoidal variation in the intensity of solar radiation, capital I, that reaches the Earth. This can be approximated by equation capital I divided by ISC equal to 1 plus 0.033 cos 360 into n minus 2 divided by 365. That is also equal to approximately 1 plus 0.033 cos 360 into small n divided by 365, where small n is the day of the year. As the distance between Earth and Sun varies little through the year due to its extra outside the Earth's atmosphere, radiation also varies. It is also useful to know the spherical distribution of solar radiation. Measurements of distribution are made and recorded by M.P. Tikakera. It will be noted, which shows spectral distribution of solar radiation intensity at the outer limit of atmosphere, that the maximum value of 2074 W per meter square, micrometer occurs at a wavelength of 0.48 and that 99% of the sun's radiation is obtained up to a wavelength of 4 micrometer. The percentage of radiation obtained up to certain wavelength is also discussed. Solar radiation at the Earth's surface. From the point of view utilization of solar energy, we are more interested in the energy received at the Earth's surface than in the extra outermost part of the atmosphere energy. Solar radiation received at the surface of Earth is entirely different due to the various reasons. Before studying this, it is important to know the following terms: beam and diffuse solar radiation. The solar radiation that penetrates the Earth's atmosphere and reaches the surface differs in both amount of the character from the radiation at the top of the atmosphere. In the first place, part of the radiation is reflected back into the space, especially by clouds. Furthermore, the radiation entering the atmosphere is partly absorbed by molecules in the air. Oxygen and ozone formed from oxygen absorb nearly all the ultraviolet radiation, and water vapor and carbon dioxide absorb some of the energy in the infrared range. In addition, part of the solar radiation is scattered, that means its direction has been changed by droplets in cloud, by atmospheric molecules, and by dust particles. The solar radiation that has not been absorbed or scattered and reaches the ground directly from the sun is called direct radiation or beam radiation. It is the radiation which produces a shadow when interrupted by an aqueous object. Diffuse radiation is the solar radiation received from the sun after its direction has been changed by reflection and scattering by the atmosphere. Because of the solar radiation is scattered in all directions in the atmosphere, diffuse radiation is scattered in all the direction in the atmosphere. The total solar radiation received at any point on the Earth's surface is sum of the direct and diffuse radiation. This is referred to in general since as the insolation at that point. More specifically, the insolation is defined as the total solar radiation energy received on a horizontal surface of unit area, that means 1 square meter, on the ground in 1 unit time, that means 1 day. The insolation at a given location on the Earth's surface depends, among other factors, on the altitude of the sun in the sky. The altitude is the angle between the sun's direction and horizontal. Since the sun's altitude changes with the date and time of the day and with the geographic latitude at which the observations are made, the rate of arrival of solar radiation on the ground is variable quantity even in the time. There are nevertheless some general points that can be made. The smaller the sun altitude, the greater the thickness of the atmosphere through which solar radiation must pass reach the ground. As a result of absorption and scattering, the insolation is less when the sun is low in the sky. than when it is higher. However, when scattered occurs, diffuse radiation constitutes a large fraction of the total received. On a clear, cloudless day, about 10 to 20% of the insolation is from diffuse radiation. The proportion increases up to 100% when the sun is completely obscured by clouds. When the humidity is high, the insolation on a cloudy day consisting entirely of diffuse radiation may be as high as 50% of insolation on a clear day at the same time and place. The intensity of the diffuse radiation seen by an observer on a clear day is not isotropic, but varies a function of latitude, time of the year, time of the day, atmospheric content and other factors. This is discussed by a number of authors. The relationship is so complex that it is seldom considered theoretically. Most often, for solar system design purpose, the diffuse radiation is assumed to be isotropic over the sky, as any other assumption is simply unwieldy for designers to use. Another justification often used for making this assumption is that the diffuse radiation is only a relatively small fraction, that means 5 to 15% of the total when the sun is not abstract cloud, and that most solar systems do not operate when the sun is obstructed by cloud. Hence, variation in the distribution of the diffuse radiation are not too important to measure most users. Next, we will discuss about air mass. It is the path length of the radiation through the atmosphere considering the vertical path at sea level as unity. The air mass small m is the ratio of the depth of the sun's rays through the atmosphere to the length of path when the sun is at the zenith. Except for very low solar altitude angle, the air mass is equal to cosecant of the altitude angle. Thus, at sea level, m is equal to 1. Here, m is equal to 1 when the sun is at zenith directly overhead, where m is 2 when zenith angle is 60 degree. Theta z, the angles subtended by the zenith and the line of straight to the sun. Small m is equal to secant theta z when m is greater than 3. When m is equal to 0, just above the Earth's atmosphere. Next, we will discuss about attenuation of beam radiation. The variation in solar radiation reaching the Earth, then received at the outside of the atmosphere, is due to absorption and scattering in atmosphere. Next, we move on to absorption. As solar radiation passes through the Earth's atmosphere, the short wave ultraviolet rays are absorbed by the ozone in the atmosphere, and the long wave infrared waves are absorbed by the carbon dioxide and moisture in the atmosphere. This results in the narrowing of bandwidth. In fact, most of the outermost part of the Earth's solar energy lies within the range of 0.29 micro to 2.5 micro. The next one is scattering. As solar radiation passes through the Earth's atmosphere, the radiation components of the atmosphere such as water vapor and dust scatter a portion of radiation. A portion of the scattered radiation always reaches the Earth's surface as diffuse radiation. Thus, the radiation finally received at the Earth's surface consists partly of beam radiation and partly of diffuse radiation. It must be realized that scattering attenuation the radiation, the exact amount of scattering and consequently attenuation depends on the atmospheric condition, which vary from place to place, and at a given place depends on the time of the day, the month of the year, and the local weather condition. Ozone absorbs mainly in the ultraviolet band. It absorbs almost completely the short wave radiation below 0.29 micrometer, and its transmittance is almost unity above wavelength of 0.35 micrometer. Water vapor absorbs mainly in the infrared band at wavelength lower than 2.3 micrometer. The outermost part of the Earth's solar radiation, that means the edges of the Earth's solar radiation by H2O and CO2 in atmosphere is strong. Hence, for the outermost part of the Earth's radiation application of solar energy, only wavelength between 0.29 and 2.5 micrometer need be considered. Spectral distribution curves. Under favorable atmospheric conditions, the maximum intensity observed at noon on an oriented surface at sea level is 1 kilowatt per meter square. At an altitude of 1000 meters, the value rises to about 1.05 kilowatt per meter square, and in higher mountain values slightly above 1.1 kilowatt per meter square are obtained, compared with 1.353 kilowatt per meter square, the solar constant in outer space. The latter values is sometimes called air mass 0, AM0, whereas the sea level, the maximum possible intensity is called AM1. The upper curve applies at the outer limit of the atmosphere. The other lower curve applies to Earth's surface during clear days of a sea level location for AM1. The curve for black body at 5900 degree Kelvin. The lower two curves are for diffuse components for some haze and clear sky condition respectively. Considering solar irradiation curve or lower and upper curve case, the atmospheric transmission factor is given as the area under lower curve divided by the area under the upper curve. For small m is equal to 1, the transmission factor is 0.633, and for m is equal to 5.0 at the Earth's surface sea level, the transmission factor is 0.276. For different values of m, the transmission factor can be determined. Thus, the length of the sun's rays through the atmosphere is of extreme importance in affecting reduction of solar intensity, and also solar radiation geometry points are more important to these solar constant measurements. Thank you.